All right, we're going to do a quick video here looking at how to utilize the kinetics of radioactive decay. How do we utilize half-lives and that first order integrated rate law and all of that. So we're going to do a sample problem here. Number 46 from the book. It says a patient is given 0.050 micrograms of technetium-99. I believe, yep, that is TC. So technetium-99, and it has a half-life of 6 hours. So relatively short half-life, probably used for imaging or something like that. And we want to know how long to decay to 1 times 10 to the negative 3 micrograms. So they're given 0.05 micrograms. How long does it take to decay to there? So what we're going to use is this equation right here with the natural log of the number of radioactive isotopes at time t over time 0 is equal to negative KT. And we actually know our n sub t should be right here. That's how many we want to get to, and we know what we started with. And we need to solve then for t. So how do we get to, or what do we need to find is t. The only thing we're missing, we have nt and n0, we don't have k. But we do know that the equation for half-life is equal to 0.693 over k, and we do know the half-life. It is 6 hours. So what we're going to do then is use that equation to solve for k. And there's my calculator. So what we're going to do is k is going to be equal to 0.693 divided by 6 hours. So what we want to pay attention to here is our units. Since we're dividing by hours, our rate constant is going to be in reciprocal hours. So a couple important things here. One, a lot of times, even though you have that first order rate law, you might have to make use of that half-life equation to also find K or to find the half-life or something like that. When you do that, make sure you're aware of the time. If this asks us for the answer in minutes, since our rate is in reciprocal hours, we're going to have to convert at the end. So just something to be aware of. Make sure you know what your timestamp is and what you want to get to at the end, or what units you want there at the end. So we're going to have the natural log of 1 times 10 to the negative 3 over 0.050. It's going to equal negative 0.1155 per hour times t. So start with our ratio there. And the natural log of that is negative 3.91. Divide both sides by that. So of course, if we're dividing by something that has units of per hour or reciprocal hours, our final thing will be in units of hours. So should be that time t is equal to 33.87 hours. And that makes sense. Again, if you think in terms of half-lives, it's going to be over 5 half-lives. 1 half-life would get us to half of that concentration. The next half-life would get us to half of that concentration. So it is going to take several half-lives before we get to that concentration there. And that kind of matches up with that. So again, this is important. We have that equation. It looked like, you know, we only had 2 of the 3 variables that we needed, but by using the half-life equation, we were able to find that other variable that was missing. And then it's like, okay, we have 3 of the 4 variables, and then it's just plug and chug, and in this case, solve for that t time. So this is just one example of how you can solve for this. Again, this problem was number 46 from your textbook. so you can check that. I'm going to talk now about radioactive dating in the next video, and then I'll do a sample problem with that. So again, for the 5 people still watching this, hopefully this was helpful. Enjoy, and I'll see 1 or 2 of you in the next video.